All right, welcome everybody to part 4 of Unit 1. And today we're going to look at deep learning. We're going to see how deep learning is part of our artificial intelligence unit. All right, so let's begin. So deep learning, as we've been learning with a lot of our AI examination over the last few parts, is a subset of machine learning, which is itself a subset of artificial intelligence. And it's inspired by the human brain's biological structure. To understand deep learning, let's go back and look at where it sits in that family tree. So if artificial intelligence is the broad field of creating systems capable of performing tasks that typically require human intelligence, machine learning, which we looked at in our last section, is that subset of AI that uses algorithms to parse data, learn from that data, make decisions, and without any specific traditional programming. So deep learning, or DL, is a specialized subset of machine learning that utilizes multi-layered neural networks. We'll be examining those more in our next part to solve complex problems. So deep learning is called deep because it uses those neural networks with multiple layers. The deepness implies the number of layers to automatically learn complex patterns and representations directly for or from the raw data, progressively extracting higher level features from that raw data at each layer of the network. While traditional machine learning might require a human to explain what a whisker looks like to help identify a picture of a cat, deep learning figures that out on its own by passing the data through the many layers of computation. So the goal with deep learning is to mimic the way that humans gain certain types of knowledge. The power of deep learning is that it excels at high dimensional tasks and unstructured data, images, sound, text, where the traditional algorithms would very much struggle. So deep learning is behind virtually every modern AI breakthrough, from self-driving cars to voice assistants to image recognition, medical diagnostic tools, to the online chatbots that we're familiar with, like ChatGPT and Claude and Gemini. So for example, with deep learning and image recognition, the first layer of that neural network might be to detect some edges. The next layer will detect it as a shape. And as it gets deeper and deeper through the layers, it will eventually get to detect the entire object, like a face or a wheel. Deep learning models continually improve performance as they learn from large data sets and can scale up with even larger and more powerful computing power. All right, so let's shift our focus now to look at deep learning and some of the models that deep learning employs. So deep learning utilizes those complex artificial neural networks, sometimes abbreviated as ANN, artificial neural network, and it trains or it learns on large data sets. So here you see the subfield. Deep learning as a subfield of machine, as a subfield of artificial intelligence. The more layers within the neural network, along with its size and variety of the data that it trains on, determines how powerful or how deep that learning model is. So within deep learning models, we can divide them into discriminative deep learning models, generative deep learning models, and large language models, sometimes abbreviated as LLMs. You can also see that maybe some models you're familiar with, ChatGPT and Gemini, fall within the intersection between two of those models. With discriminative learning models, or discriminative deep learning models, these models learn the relationship between input and output. They ask questions like, is this an A or is this a B? It's going to choose or discriminate between them. They're commonly used for learning boundaries between classification, like fraud versus not fraud, or prediction tasks. They map those inputs based on labeled training data. They do not generate new data. So a discriminative learning model does not generate data, it discriminates or chooses and makes decisions. An example would be determining, again, whether an email could be considered spam or not spam. With a generative deep learning model, these models learn how data is structured. So they're looking for patterns, and from the generative deep learning models, they can generate, hence the name, new data. So they ask questions like, can you make something like this, like A? So it will build you something new. They model the underlying distribution of that training data. So examples would be where we get it to generate an image or generate music or human faces or text. So a generative adversarial network, a GAN, uses a generator and a discriminator to create something and make it appear. A variational autoencoder, or a VAE, learns how to take complex data and simplify it, or recreate, or create something entirely new. And a diffusion model, right? Or for example, what's called a stable diffusion, or a good example is this is the DAL-E model, which comes out from OpenAI. That model diffuses an image into static, and then it learns how to reverse engineer it. So those are some very specific examples, but the key point here is a generative deep learning model is going to generate new data from the patterns it's learned. And then finally, the large language model. Those are kind of also generative, right? They are trained on massive data sets. So there's some overlap. They're not really necessarily that distinctive categories. There's overlap between the LLM and the generative and the discriminative. But in general, a large language model asks questions like, well, what comes after A? So now it's a predictive model. It's predicting, often very much predicting text, whether it's spoken text or written text. It's determining and predicting context. It's predicting language. They might predict the next word in a sequence of words and then generate coherent text. So these models just keep predicting what would be the most likely word next in a series of generated text, pieces of text. They perform reasoning, they do summarization, they do translation, and even conversion or conversation, I might more accurately say. So LLMs are pre-trained on very large sets of data to classify text, to answer questions, to summarize documents, and even to generate text. So then they're fine-tuned for specific purposes. So for example, an LLM can be fine-tuned for finance or healthcare or retail. Some examples of modern LLMs, I mean, we know them. They're things like ChatGPT. They're things like Claude. They use something as well called a transformer architecture, which learns to understand relationships of the parts of a sequence, like the words in a sentence. And the transformer figures out which I should give attention to, which parts of the sentence are more or less important, and this helps predict context for the words themselves. So again, this is a lot of detail here. The goal again is to get a general understanding of the large language model. So a large language model is a pre-trained model on large data sets that is very much specifically for language-based tasks and for predicting things like what word comes next in a sequence, which makes for things like conversation with these models quite possible. Okay, so let's look at the deep learning and the personalities of AI. So I'll put that in quotes, and how to distinguish between these model types. So we'll look at the model type, its purpose, and an example. So let's start with discriminative models. What's its purpose? Well, the purpose of a discriminative model is to classify or predict by drawing a line between categories, to put things into categories. So examples of discriminative models are facial recognition or spam filters, filtering out what is spam and what is not. They classify or predict a label. Generative models, they're going to create new data that looks like the data that they were trained on. So if they were trained on pictures of cats, they can generate a new picture of a cat. So examples of that is Midjourney for images, or some classic deep fakes on the internet, right? Or Google's new Nano Banana image generation model. Large language models specialize in generating and understanding natural language, whether written or spoken, the large language model, its purpose is a massive, both generative model for predicting sequences of text. So obviously all the major ChatGPT, Gemini, Claude, those are large language models predicting text because you're typing in them or you're speaking to them and it's predicting what you want it to say next. So a discriminative model tells you a picture is a cat. So a discriminative model will go, that's a cat or that's not a cat. A generative model will draw you or create for you a picture of a cat. A generative model goes, oh, I know what cats look like. Here, let me create a brand new picture of a cat for you. And a large language model, well, it's language. So it'll write you a poem about a cat. The most common AI models, ChatGPT, Gemini, Copilot, Claude, etc., they intersect between generative and large language. They can also do discriminative tasks as well. But in general, those models are designed to be generative. That's why we go onto those models and ask it to create things for us. But they're also able to communicate with us through that large language model process of generating and predicting text. So let's go over some ways you can tell if it's not a generative model. Well, if the output is a number, like it's just giving you a number or a classification, spam or not spam, or even a probability, which I guess is also a number, but something like there's a 30% chance this is a picture of a cat. Now, you can tell if it is a generative model if it's outputting natural language to you. So it's essentially talking to you through text or through speech, or it's outputting an image to you that you ask it to generate, or audio, or even video. The generative model generates new data similar to the data that it was trained on. So we could talk about text to text, where natural language is the input and it produces natural language as the output. So typing in a prompt in ChatGPT gets it to spit text onto the output for you. Text to image, similarly, where we give it an input of, say, trained on large images, and it would generate new images for us. Text to video, the same way, except now we're talking about video generation. Even things like 3D models for gaming assets or 3D printers, or text to tasks, where it's performed specific tasks that it's been trained on, or actions through AI agents. All right, again, we want to get a big picture look at this and not dwell on the specifics. So let's return and talk about a related concept, training data. So deep learning models, just like machine learning models, train on the same sort of data and learning paradigms that we saw in the previous section of this unit. So that would be supervised learning using labeled data. So when you give it the answer key, thousands of photos that are labeled or tagged as hot dog and not hot dog, it will learn right from that labeled data. Each training example includes an input matching with a correct output label. And then it also trains on unsupervised learning, which uses unlabeled data. That model looks for patterns on its own without being given what it is, without being told what the label is. So it now groups, for example, customers by their shopping habits. This algorithm will discover patterns or structures without the labels in place. We can also introduce semi-supervised learning. This is kind of a hybrid between the two, a best of both worlds approach, using a combination of some labeled data and some unlabeled data. You use a small amount of labeled data to guide the model and train the model, and then apply the rules to a massive amount of unlabeled data. This is a very common approach when the labeled data is very expensive to create, right? So if we don't have a lot of labeled data, we can create a small amount of labeled data and use the semi-supervised learning approach. Modern AI and deep learning models are shifting more towards those semi-supervised learning models to handle that massive amount of data on the internet that is obviously not labeled. All right, let's now dig into some specific details of deep learning. So we're going to take the deep learning models and organize them into three distinct types of layers. Let's say we have an input layer where the raw data, the pixels, the text, the prompts, the words, that's going into the system. So for example, a picture of a dog goes into our model. Then we'll skip ahead and let's look at the output layer. It's going to output a result like this is a dog. and it has maybe a confidence rating, like it's 98% confident that this is a picture of a dog. What's going on in the middle are the hidden layers. This is where the learning happens. Those are the layers that will extract features like edges and shapes and textures, and then based on it, will make those types of discriminative or sort of predictive sort of features start to come out as it gets closer to the output layer. We're definitely going to go over this in more detail when in our next section we look at neural networks. Okay, so how does a network know that it made a mistake? Well, the answer to that is the concept of backpropagation. So what backpropagation is it's the main learning algorithm for deep learning where the model calculates prediction errors. This is also where the idea of the iterative looping process comes in. So errors are propagated backwards through the network to update the model and improve accuracy. So let me give you an analogy, right? Let me give you an analogy at how backpropagation could work in its general form. So let's pretend you're an archer and you're trying to shoot a bullseye. So your first shot is kind of like your prediction. Did you get it right? Probably not, right? So you shoot your arrow and you miss the bullseye. So then what we look at is how much did we miss the bullseye by? That is essentially a calculation of our error or how much our loss amount, our loss error. So the correct answer would have been a bullseye, but we didn't get a bullseye. So then we move backwards. We think, well, wait a minute. The reason I didn't shoot the bullseye is, well, maybe I shot too high because I need to adjust the angle of the bow and the arrow and adjust the tension of how far back I pull it, which might mean I have to adjust the angle of my elbow as I pull it back. So I'm essentially going backwards through the process of shooting that arrow and making subtle adjustments to the stages. And then I shoot again. And I see, did I get closer or did I get further away? And then I go again and I go back through the process, back propagate, to calculate how much each part contributed to the error and guide the adjustment towards getting closer and closer to the bullseye. As I get closer to the bullseye, I no longer need to keep refining back through the model to see how far I need to change something like how high my elbow is pointing. So I hope that analogy kind of makes a little more sense, what kind of backpropagation is. But let's go further. So in step one of backpropagation, the forward pass, the network will make a guess or a prediction. So our deep learning model will make a prediction. This is a cat. Step two, we have a loss function. We'll calculate if it's not a cat, how far off are we? Was our prediction that it was 90% a cat, or maybe 50% it was a cat, when in reality it was 100% a cat? Okay, well, if we guessed 50%, we have to make 50% changes to get better at this. If we made a prediction of 98% it was a cat, we only have to make 2% of a change. So then we move to step three, the backward pass. This is where the word back comes from in backpropagation. The network will walk backward or propagate backward through the different layers, adjusting weights and biases. We'll look at what those are in our next section. Essentially, it's adjusting little details, like turning little knobs to make adjustments to reduce the error. So this is what's called gradient descent in statistics. So the next time it makes a prediction, so if it predicted 50% it was a cat, maybe this time it'll predict 65% it's a cat. And then the next time through 75% or 85%. Backpropagation enables the learning to take place through those gradient upgrades each time it's getting better. So here's another analogy. A team of people are passing a message down a line. And then you go and check that final message against the original message, like a game of telephone that we used to play in elementary school. Go back to each person and say, well, what did you mishear here at each stage? And tell them, okay, well, listen more closely to this part next time, and then try again. So it's yet another kind of analogy to kind of give you a general idea what the concept of backpropagation is. All right, everybody. That concludes this section, and I hope you found it useful, and have yourself a great day.